Finally, we're in the position to derive the equation of motions of the field, of the electromagnetic field, and we are going to see how it evolves as a function of time, and finally obtain the solutions for the field equations in terms of retarded potential. So we are going to proceed as usual, in the sense that we are going to define a Lagrangian density for the field. Once we have the Lagrangian density of the field, we can construct the action that we want to minimize. Therefore, we go through the least action principle to minimize the action and derive the equation of motions. Okay. Then, once we have the equation of motions, meaning the field's equations, we can use an ansatz to find an actual solution for those equations, and therefore express it in terms of retarded potentials, as we are going to see. Okay, let's get started. Okay, equations of motion of the field. So the analogy is, so the procedure is exactly like the one for particles, or for any physical system, for any classical system. And I just remind you that a particle is characterized by a mass, a charge, for instance, which are constant properties of the particle, and the position and time, expressed here by x mu. Okay. Now, when we go for the equations of motion, the variable that we are interested in is hidden in this x mu, because we want to know what is where the particle is moving. Therefore, we want to trace x mu. Okay. Is actually r, because there are more than one components, are the variables. Okay. If we have a field, as for example based on the 4 potential like the electromagnetic field, we have a mu, which is equal to phi a bar. Okay. The variables here, even though we have that phi is expressed as a position in time with respect to x mu, and a bar again is expressed for a certain position and time, the variable is not x mu. The variables that we are tracking are phi and a vector. Okay. You can imagine the position here as a label, if you wish. So you're asking yourself, given a certain position in space, how the potential is evolving as a function of time. Okay, I made the example of the temperature a few lectures ago, where I just said, okay, I want to know what is the evolution of the temperature on Earth. So I'm asking myself what is in a certain location the temperature at a certain time. So I'm studying the evolution of the temperature here for all positions. So here, and so on and so forth. Okay, therefore the point is not that the temperature is going somewhere, as it was the particle, if you wish, but we are just asking ourselves for all positions, for example this one, how the field is evolving. Okay, this is a conceptual step that sometimes is a bit, people kind of lose it. Okay, even if it's quite obvious. Okay, good. So let's get started, and as usual, the path is to define a Lagrangian density on which we can build up our action, go through the least action principle to find the equation of motion that then we want to solve. This is the path, usual path. Okay. As for the particles, when we derive the Lorentz force, for example, the Lorentz force, we arrive up to here. Okay. Good. So let's get started. We need to define our Lagrangian density. Good. What the Lagrangian density, well, actually just to give you a connection with the Lagrangian density to the action, we have our action S, that's equal to the integral of the Lagrangian density over the volume over the T, where this guy here is our Lagrangian. Okay? But it is something that you already know. Okay, so we want to build our L, and as I already mentioned when I introduced electrodynamics at the beginning, when we wanted to build up the theory, the Lagrangian, the theory that we want to create, must obey some constraints. Okay, it must some criteria, because the theory must reproduce what we observe in real life, which is, for example, which for example in electrodynamics is the Gauss force. Okay, for example, we must reproduce Gauss force. Okay, the Gauss law, better to say. Then we want to respect the superposition principle. Because we know that if we have a charge producing a field, and we have another charge reproducing the field, and another one, and so on and so forth, we know that each of them are solution for the field for each charge. So this potential is the solution for this charge, and so on and so forth. And we know that the total solution, which is given by the sum of all the potentials. So whenever we have the solution for one of the charges, and we have more charges, the total potential is given by the sum of those potentials, of those solutions. Okay, which means that our Lagrangian must be of quadratic form. Because I already gave the simple case in which, I don't know, we have a quadratic equation. When we make the derivative of this the quadratic equation, we get something which is linear. Okay? Therefore, when we apply the least action principle, and we have a Lagrangian which is of quadratic form, whenever we make the variation of the potential, the second power, if you wish, comes down and it becomes linear. Don't take this one literal, okay? This is just to let you understand the idea, the principle of that, why it has to be quadratic to have a linear theory. Okay? Linear theory, and therefore the superposition principle. And then it has to be an invariant. We have seen which kind of invariants are related to the field, which is expressed by the f mu nu. Okay, so the field is contained in this tensor, which is antisymmetric. And one of the invariants that we have, actually the invariants that we have that then allows to fulfill all of these requirements is f mu nu, which is equal to 2b squared minus e squared, as we have seen. Okay, therefore the Lagrangian must be based on this quantity. So we are going to have f mu nu, multiplied by some constant. Okay, how do we choose the constant? Well, we define the constant such that we have Gauss units, for example, 16 pi c, and then there is going to be, so this is to have Gauss units, and then we have a minus, because hidden in here, you see, so this is basically f mu nu, so this is basically 2b squared minus e squared. Okay, so imagine that here you have this b squared minus e squared times 2. Okay, so you see that here there is the electric potential and the electric potential is related to the 4 potential as 1 over c dA bar over dt minus gradient of phi. It means that if we plug in our potential in here, so the electric field here, we are going to have the square of a time derivative with respect to A. But in principle, we can have electric field that are changing with an arbitrary velocity, and therefore the second this derivative here, the square of this derivative, can be extremely large. And if it is extremely large, there might be it might be the case that we don't get a minimum for the Lagrangian, okay? That we must have for the action, sorry, that we must have, because otherwise the equation of motions wouldn't exist. Okay, so it must fulfill the least action principle, the action that we are going to derive. Therefore, that's why there is the minus, so that we are sure that there is a minimum. Okay, good. That's it. And yeah, this one to be quadratic. So now if we put all what we have together, because whenever we have our system, we might have charges, and it plays together with the field. Therefore, we can have the 16 pi c f mu nu f mu nu, and then there is the contribution of the there is also in the Lagrangian, we are looking for the total Lagrangian of our system, and there is also the interaction between the charges, sorry, the field and the charges, J mu mu. What's that? Okay. So this represents the self-interaction of the field. So you see, it's the interaction of the field with itself. Whereas this guy here represents the interaction field matter. Okay? And again, you see that all of this is invariant, because this guy is an invariant quantity, as we have seen, and this guy here is a constant because of charge conservation. I remind you that the mu j mu is equal to 0, okay, which expresses charge conservation. Therefore, this object is a valid Lagrangian, and it fulfills all the constraints that are necessary to derive all the electrodynamical properties that we see in experiments. Now that we have our Lagrangian density, and we have our action, which is based on it, we can continue and apply the least action principle. We basically impose S equal to 0. Now, I am not going to go through that, because by now you should already know how to do it, because we did it for the charged particles, plus there is going to be an exercise about that. Okay, so you will do it yourself. It should be no problem for you. Anyway, we plug, the idea is that we plug this one, our action that we know from before, in here. That's the action, that's the Lagrangian density that we have, and we plug it in. We plug it in here, and we basically obtain the Maxwell's equations. So we have the mu f mu nu equal to minus 4 pi c j mu. Okay, or if you wish, so let's stick to this one, take care of the minus signs, because for example we could also write it as df nu mu equal to 4 pi over cj mu. Because I flipped the indices here, f is an antisymmetric tensor, and therefore the minus disappears here. Okay, so take care, sometimes you see them with the minus or not, so take care of how the indices are flipped one with respect to each other. Good. So just list action principle, you know how to do it. There are a few tricks that you already done, and then we solve them. These are 4 linear differential equations, inhomogeneous, because we have a source term here, which is given by the charges, by the force current. So the charges are expressed through the force current. And the first thing that you want to do in solving a linear differential equation is to solve first the homogeneous equation that is associated to it. Solve homogeneous equation. Okay, so we have our d mu f mu nu equal to 0, and we know that this is constraint is equally 0 because of the antisymmetry of the 4 tensor, because we know that the nu f mu nu is different than 0, so the different components that are antisymmetries are different than 0 if and only if nu is different than mu, let's do it the way around. So we have the alpha f mu nu equal to 0. This is identically satisfied because of the antisymmetry of f, where this notation here stands for cyclic indices, which basically mean that I have the alpha f mu nu plus the, and then you rotate the indices, so you bring the mu here, then you have f nu, and alpha cyclic goes on the back, plus the, and again cyclic, nu moves there, f alpha shifts, and mu goes on the back, equal to 0. Try out if you plug in f here. Because if it is an antisymmetric tensor, you will see that this is equal to 0. But then what do we have? We have that our derivative f mu nu is going to be different than 0 if and only if the alpha mu nu, I used alpha, is different than mu, which is different than nu. Okay, and this leaves us with 4 independent equations. Which makes sense. I mean, it has to be, because you see you have a nu, you have the summations here, and you are left with an index which is mu and mu here, which respects to a 4-dimensional vector, and therefore 4 linear differential equations. Okay, fantastic. Now, to have the solutions, to have them written in explicit form, you just need to look for the components, and for example, we can set mu equal to 0. So we look for so we make it explicit. We look for the time component, which means we set mu equal to 0. Yes, mu equal to 0, and then we have the symmetry, so we have the terms that are sum up with respect to nu, and we get the b equal to 0. Then we look for the space component, mu equal to I, 1, 2, and 3, and we get time variation of B plus C gradient cross E is equal to 0. So these are the gas Faraday law, okay, laws. Perfect. Once we have that, we can proceed and then look for plug in the 4 potential into our equation here. Let's call it star. So we can plug A mu in star. Okay, if we do that, what we obtain is the following equation: the A mu equal to minus 4 pi over C J mu. You can just plug it in because F is expressed in terms of A. And this is the D'Alembert operator. Which is nothing but, let's define as d nu, which is equal to minus d0 squared plus the gradient squared. Okay, which if you want to be even more explicit, that is equal to 1 minus c squared d over dt plus the gradient. Okay, where again you see the nu, so that's the derivative with respect to x mu, derivative with respect to x mu. There is the metric embedded in, and therefore you get this minus in the first element of the symmetry. Okay, and then you have the space component. Good. Now that we have that, we can start with our ansatz and look for a solution that respects the superposition principle. It was D, maybe C, E, so last D, E. Step E, we plug solution such that anti-solution must allow for the superposition principle. Okay, and therefore we solve it. So we solve the equation, this one, in terms of green functions, actually in terms of retarded green functions. Okay, what does it mean? Now I just explain you term by term how the solution look like. So our A mu, given for a certain position, given for a certain time, is equal to 1 over c. Then we have the integral over the x prime, integral over the t prime of g t minus t prime x minus x prime j mu x t prime prime. Okay, superposition principle. Look at this. We have a symmetry. So we have a symmetry of the contribution of all the source of the potential. What are the source of the potential? Are point sources. You see, this is a charge. So this represents a charge with a certain density G, with a certain current J, and you see you are summing the contribution of all of those particles. Okay, so this basically stands for the superposition. See, linear superposition. An integral is a summatory of the function that you have inside, so of the particles in this case, for a continuous scenario, okay, for many particles, and this makes it this gives this integral. So this represents the linear superposition of particles. The prime here is the time and the space for the observer, and the green the green function g t minus t prime x minus x prime is equal to 1 over x minus x prime delta t minus t prime minus x prime modulus over c. Okay, which totally makes sense. Why is that? Because this guy here represents Coulomb's force, potential actually, right? So you see, a charge gives you a contribution of a Coulomb potentials. All charges are summed up together. Then what is all of this stuff here? Well, it is a delta for this argument, which means that this function is equal to 1 if t minus t prime minus x prime over c is equal to 0. What does it mean? This means that the t, then I bring the c and I put it here, and I bring the x minus x prime modulus on the other side is equal to the modulus the x. Okay, what's that? Does it sound familiar? Does it look like the light cone? Because what we perceive as a potential in a certain position is basically given by the contribution of all of the particles that are living on the back light cone. Right? Because if I am here, Ct x, this is the light cone, I have a charge here, and I can feel its potential only when the signal, when the potential had enough time to propagate and reach me. Because potentials, as well as anything, cannot move faster than the speed of light. They are massless, they move at the speed of light, and therefore they are traveling along a light cone and they reach us. Therefore, what I'm going to perceive perceive here is the contribution of all the particles that are at a certain time that arrive together in that time to me from the past. Okay, so this guy here stands for that. So this basically represents is the delta function that tells you in space and time these are the particles that contribute to the potential that I perceive at a certain moment in a certain location in space. Okay, that's why one speaks about retarded Green's function, because it contains the concept of the fact that the potentials arrive delayed, arrive retarded. Okay, one have to account for the delay of the propagation of the potential. Good. Now that we have our solutions, go back a second. So now that we know what are the now that we know that we need to solve this equation through retarded Green's functions, because of the reason that I mentioned, because they satisfy Coulomb's potential and they also respect retardation, we just plug them So we have A mu, so we have A of mu, which is that we know how it's explicitly expressed, and we just plug it into our field equations. And we just obtain, this is step D, F, sorry. Okay. We basically plug our A mu in field equation. Okay. So now keep in mind that, as I said, the superposition principle is characterizing a particle. So you have this J mu is a point source that we can express in this way. G mu, we have already seen that, Q C V delta of R minus R0. Okay, so you see it is a continuous function, because it is expressed as a continuous function, but this function contains the J, so the four current of one particle. You see there is Q, is not a density, is Q, is one particle, multiplied by this delta function. So this function is equal to 0 everywhere except where the particle is. Okay? Good. By using that, by plugging our A mu into the in our equation, we finally find out what are the retarded potential phi RT equal to Q R1 minus E beta, and then A RT equal to Q beta R1 E beta, which is equal to Q phi. Sorry, to phi beta. They are the same, you see, except that there is a beta here. Perfect. Okay, so these are our retarded potential, and now I just make a drawing, because the geometry is a bit might be confused, because you see here in the integral we are mixing the position where I am perceiving the magnetic field. We have the position of the observer, and we have the position of the charge. Let's make some graphic, because so that you have a better understanding of what's going on. So if we keep the origin of the frame here, for example, the observer is located here. Oops, sorry, then I recenter it here. So this is going to be R, so that's the position of the observer with respect to the center of the frame. We have a particle which is somewhere, let's say here. So we have one charge here. This is going to be R0, you see, here. This is going to be the separation between the observer and the charge, big R. So you see R is the modulus, so this represents the separation between the observer and the charge, and the particle might be moving, I don't know, in this direction. Okay? Particle velocity, remember that P is equal to V over C. Okay, so that's the scenario. We are here and we perceive the potential of this charge after a certain time, where the origin of the frame has been set in a generic location here. Okay, now keep in mind that when we are doing the evaluating the potential, when we derive the electric and the magnetic potentials, electric fields, sorry, It depends on derivatives. So we are going to, with respect to the vector potential. So they are expressed in terms of gradient of phi and time derivative. You see delta 0, so that's d over dx0, so it's a time derivative of a bar. Okay, so here you see that there are derivatives, but these derivatives have to be defined with respect in terms of the observer's coordinate. Well, coordinates, observer frame. Okay, after you do that, to have an explicit relation for these potentials, the last one, which is the FG, last step, we make an approximation. And we take the approximation that the charge is very far from the observer. Okay, so, or if you wish, we are assuming that the observer is very far away from the charge. Approximation. Observer is far away. In this way, we can basically simplify the derivation, because we can drop all the terms that drop faster than r to the minus 1. So you see we have an r, and we have an r minus r times this scalar product, okay, between e and beta. Therefore, if we basically stretch the position of the observer, so we set the observer very far away with respect to the charges, which is the case in astrophysics, because we are dealing with astrophysical sources. Imagine you have a galaxy, something is happening on that galaxy, there is a charged particle moving, and we are observing from very far away. Therefore, the motions and the angle that we are going to see are always within very, very small separations in the sky, and therefore we can, this approximation is a very good one. Okay, and basically what we do, we drop all terms that have an order higher than r to the minus 1. Okay, which basically is this guy here. Okay, so basically it's a first order approximation, and in doing that, the potential, let me copy it, so far, so just to stress the fact that this is an approximation, even though a very good one, rc 1 minus e beta to the power of 3, and then we have e cross e minus beta cross beta dot, and then we have for the magnetic field b phi equal to same business, rc 1 minus e beta power of 3 e cross beta dot plus e beta cross beta dot. Voila, where E is defined as R over R. Okay, so that's the direction where the photon is coming toward us. Okay, so this is the final result. Let me give you a little summary. So the scheme is the following. So we start with the Lagrangian, we define the action, we minimize the action using the least action principle to derive the field equations that then we want to solve. The Lagrangian density is constructed by two parts, one which represents the field-field interaction, so this is the self-interaction of the potential. So this guy refers to a potential, an electromagnetic potential alone. Okay, where we have seen that it has to be of quadratic form to have linear differential equations as solutions for our theory, so that the superposition principle can hold. The constants here are related to are set such that we need the unit of measures that we want. The minus guarantees to have a minimum for the reasons that I explained. And then we have one second component, this one, which relates, which expresses the interaction between the field and the particle and matter. So you have the field-matter interaction that we already described when I've shown you the equation of motion for the charged particles in an electromagnetic field. We have our Lagrangian density, therefore we have our action that now we minimize and derive these four linear differential equations. Okay, no surprise, because we started with a Lagrangian that had a that is of quadratic form, where we have that the field is sourced by J mu. So the source of the field is not the charge, but is the force current. Okay, not only the charge, is the force current, is the source of the field. Then we go, this is a set of linear differential equations, therefore we first solve the homogeneous equations. Then we want to move in the direction of deriving the electric and the magnetic field, therefore we express the electromagnetic tensor in an explicit way by using its definition based on A mu, which basically transforms this equation into this one. The box operator here is the D'Alemberto operator. Then, in solving to solve this equation, we just have this. We just use this solution, so we know that this is the solution of this equation, because this equation can be solved in terms of green functions, where this term of the green function basically shows you that it is the Coulomb potential. You see 1 over r, or the distance, that's the Coulomb potential, which is active with a delta function, meaning that we received a potential of the form of a Coulomb potential that is coming from a certain position at a certain time. And this accounts, with this trick, one accounts for the retardation of the signals. And so now you see that basically G times J so expresses the contribution of one charge, and the integral gives the sum of all charges. So this summation here represents the superposition principle of individual charges that produce a Coulomb potential. Then what we do, we just have our solution, we just plug it in here, and we find the explicit form for beta and alpha. So we now have the solution for the potential. Now what we want in the end is the electric and the magnetic field, and therefore we just use the definition of the electric and magnetic field, which is basically a combination of derivatives of the components of the four potential to derive the final form. And here, in doing that, we made an approximation in which we assume the observer to be very far from the charges, which is the case in astrophysics, because we are observing, for example, galaxies or the gas distributing within our galaxy, which is very far with respect to the sources one from each other.